Okay, good morning. Let's start. Let's continue from the content we had from Monday. So we're going to show a combinatorial identity for this R is integer between 1 and n. We want to show n choose R equals the right-hand side, which is the sum of these two binomial coefficients. Here we offer two kinds of proof. The first one is called algebraic proof. It's basically you simplify the two expressions and show they are identical. So we'll start from right-hand side, which is more complicated, and we simplify it. So write down the n-1 choose r-1 by their definition for this expression. We get this is n-1 factorial over r-1 factorial times their difference factorial. Then n-1 choose r, this is n-1 factorial times r factorial, then their difference factorial. So n-1 minus r factorial, let me write down as n minus r minus 1 factorial, the same. Then we combine this sum and then simplify it. And just recall a little recursive relation mentioned last time. This integer m factorial equals m times m minus 1 factorial. So if we want the sum has a common denominator, just look at comparison. So in the first one we have r minus 1 factorial, the second one we have r factorial. So if we add an extra r together with r minus 1 factorial, this can be combined to have this r factorial, but we need to also multiply r in the top to cancel it. So this together is r factorial. And similarly, for the part with r minus 1 factorial and n minus r minus 1 factorial, by this recursive relationship, we just need to multiply n minus r to n minus r minus 1 factorial and to create the same factorial. So also multiply this to the numerator. Again, this is n minus r factorial. So we now have the same common denominator, which is r factorial times n minus r factorial. And then we sum up the numerators. We have common factor n minus 1 factorial, so I just take it out. And just multiply r plus n minus r. So the r minus r is canceled. We have this n times n minus 1 factorial. This is n factorial. And then it becomes this expression is exactly n choose r, which is the left-hand side. So this is our algebraic proof. We use algebraic operation to simplify expressions to show they are the same. For this one, it's convenient because it's not very complicated. And we also offer a combinatorial proof. Basically, we want to create a scenario that both sets count some kind of number in different ways, so they are the same. So we want to create bijections. Essentially. So in the combinatorial proof, we don't need to simplify a lot of things. Just mention that these two sides are different ways counting the same thing. So the left-hand side, n choose r, we know the meaning for this binomial coefficient. This is a number of ways to choose r atoms from n distinct objects. So let's just assume these numbers 1, 2, up to n. Okay, we show the right-hand side is also such a number, but we count differently. Let's also choose our items from 1 to n. You can do it in different ways, so we consider different cases. So for example, we count in terms of a certain number is chosen in these R atoms or not. For example, we consider the case that this 1 is in these R chosen atoms or not. So there are two cases, and we count them. Each case gives a binomial coefficient. So case 1 is this particular number. You can also choose n, 2, whatever you like. So this 1 is not, or is, maybe start with 0, is among the R chosen numbers. In other words, we have fixed 1 in this R atoms chosen. We choose the remaining R minus 1 atoms. So the number of ways for case 1 is, this number of ways is, we have n minus 1 number to choose from, and then we choose the remaining R minus 1 numbers. Okay, assume n is this 1 must be chosen. The second case is this number 1 is not chosen. So we are not going to choose 1 among our atoms. So we choose, so we have only n minus 1 numbers to choose from. We choose from 2 to n, and we choose R numbers out of them. So it's n minus 1 choose R. So basically, we are counting the same thing. So we have these two numbers are the same. So in the combinatorial proof, we don't really need to actually exactly compute something or write down the exact expression. We just create this kind of projections. Okay, let's move on to the next theorem, still about combinatorial identities. So the next result is called the binomial theorem. The statement is here n is a non-negative integer, 2, 3, 4, 5, this kind of integers. Then you have this expansion of x plus y to the power n. X, y are arbitrary numbers. This can be written as a sum as this index k from 0 to n of this kind of summons n choose k times x to the k times y to the n minus k. So this is an important result. Let me circle it, let me box it in red. We also use this kind of result later on. We talk about random variables. So because of theorem, so this n choose k is often referred to as a binomial coefficient. Because of binomial theorem. Okay, so let's offer a proof for this result. So we can always start with the simplest result. So we know that x plus y squared, this is how you expand it is you write it as x plus y times x plus y. So write it as the product two brackets, each of them is x plus y. And when you expand it, each bracket, you multiply the atom contained in each bracket with one each other. So when you do the expansion, each bracket will either contribute to x or y in the product. So you have x squared come out if the two brackets both contribute x. And you have this cross terms x times y. If one bracket contributes x, the other contributes y. And also you have this y squared. You both contribute y. And their coefficient in front of them can be given by their binomial coefficients. So if you want both of the brackets to contribute x, so we'll choose two brackets out of the two to contribute the x term. And to get the cross term, we choose one of the brackets out of the two to contribute x. The other one automatically contributes y. So we have to choose one in front. And for the y squared part, we choose 0 of the brackets to contribute x terms. So get to choose 0. If we interpret n choose k, we choose k brackets to contribute the x terms in their expansion. So similarly, we have x plus 1 plus y cubed. This is the product of three brackets. And similarly, you will see the summons as x cubed if all the three brackets contribute to x. So the number of cases is you have three brackets, choose all of them to contribute to x in their expansion. And we can also have x squared times y. This means we choose two brackets to contribute the x term. The remaining one contribute y. So we put 3 choose 2 in front it to this is a number we can get x squared times y. And then we can also have x times y squared. So this is the case that we choose one of the brackets to contribute x. The remaining two contribute the y term. So again, this is 3 choose 1. And then for the y cube, we choose none of the brackets to contribute x term. And you can see the pattern here. Then we can generalize this kind of counting method to reduce the theorem. When you have x plus y to the power n, now you are looking at the product of n brackets. And the summands always look like the term like x to some power times y to the some power, and their sum of the power equals n. So you can assume in general it looks like x to the k and y to the n minus k. So how many ways we can obtain a summand like x to k, y to n minus k is that we just choose k brackets from these n brackets to contribute x terms in the expansion. So we'll get n choose k this number of ways. And the remaining n minus k brackets, we just assume they contribute the y terms automatically. Okay, so that's how we prove the theorem. Okay, now let's use the theorem to work out some examples to get familiar with that. In the first example, let's find out how many subsets are there of a set consists of n elements. Okay, here I also just provide two proofs because for counting method, you can always have different ways of showing that. I just want to mention more methods to broaden our viewpoint. So the first method, let's try to apply the previous binomial theorem. We count directly. So we count how many subsets are there of a set. In this set, we have n elements. So we can think of we choose subsets from the set composed of 1, 2 to n, this n numbers. So we count in terms of the size of subsets. So because this is exact binomial coefficient, so the number of subsets of size size k, chosen from the n distinct subjects is exactly, so from this 1, 2 to n, this n distinct subjects is exactly this binomial coefficient, and choose k. Okay, just choose k items out of n distinct objects. And then total number of subsets is, and I should mention that this k can be 0, 1 to n. If the size is 0, this is empty set. So total number of subsets is we sum over all these subsets with size k, and k is from 0 to n. And then this looks familiar if you compare with the binomial theorem. So maybe I just write down here. This binomial theorem that you have xy plus y to the power n is the sum, also k from 0 to n, and choose k, x to the k, y to the n minus k. So the right-hand side is already similar to the sum of n choose k. Now we set x equals y equals 1, you get exact expression. You get this 2 to the n equals the sum of n choose k, where k from 0 to n. So you know this summation has a closed form expression is 2 to the n. Okay, we can also just count in a different way. We can also find this 2 to the n immediately. So what we do is that we sort of create a bijection by counting different subjects. So for each subset of this n elements, this numbers 1 to n, we are going to find a representation for it. So what we do is that we create a string of size n. In general, each of the string looks like a list of n numbers, x1, x2, xn. And here, just values. In general, each xi is equal to 0 or 1. So we assume it takes values 1 if this number I is in the subset. and 0 if this number I is not in the subset. So we write otherwise. So for example, to be concrete, so the empty set, so it contains nothing is none of the integers is in their string, so we get 0, 0, and zeros. And if your set is 1, 3, then it corresponds to string like x1 is 1, x2 is 0, x3 is 1, and all the others are 0. So you can see each subset has a unit representation in terms of the string. So it's equivalent to count the number of strings we can form. So number of subsets is equal to number of such strings. And to count number of such strings, you count, so for each position, xi indicates two values, 0 and 1. So for x1, it has two choices, x2, two choices. So just multiply these two together, n times, you get 2 to the n directly. Okay, so for the next example, I want to show this identity that the sum of k from 0 to 1 minus 1 to the power k times n choose k equals 0. So if you want to try to simplify the right-hand side, it's very complicated. But you can recall that if you have the sum of n choose k, this kind of expression, this is always related to the binomial theorem. So maybe copy it here. Okay. So the right-hand side is already similar to the identity we want to prove here. We just need to create this minus 1 to the power k. So we can see that if we set y equals 1 and set x equals minus 1, this is exactly identical. So just set x equals minus 1 and y equals 1 in the binomial theorem. We get this is k equals the sum of minus 1 to the k, n choose k. This is equal to minus 1 plus 1 to the power n equals 0. Let's see another example. This one asks to show this identity, n choose 0 plus n choose 2 plus n choose 4. So plus this n choose even numbers is equal to n choose 1 plus n choose 3 plus n choose 5 plus n choose all numbers. So on both sides, it looks like infinite sum, but actually we said that we always assume n choose r equals 0 if r is bigger than n. So you have to stop at some point. It's both finite sum. So this is actually identical to the previous example because let's write down the previous example. We show that 0 is equal to the sum of k from 0 to n minus 1 to the k, and choose k. So if you have minus 1 to the k from 1, 0, 1, 2, it's interlacing summation, it's interlaced between plus minus 1s. Let's write it down. This is k equals, start from 0. So you get n choose k, then k equals 1, you get minus n choose 1, then k equals 2, you get plus n choose 2, then minus n choose 3. You can see that. So it's so we have the minus n choose odd numbers with the positive n choose even numbers. This together equals 0. So we just rearrange the terms. Move the negative terms on the right-hand side to the left-hand side to prove the identity. And of course, this is sort of an algebraic proof for this kind of question. We related to the binomial theorem and apply the binomial theorem. So I will just leave an extended exercise. So if you are interested, you can try to prove this identity by providing a combinatorial proof. So exercise, can you provide a combinatorial proof? Basically, we want to show that both sides are counting the same objects using different methods. Okay, so before we move on to other things, I want to mention that our this question and answer part will be given on this platform called Add Discussion, which I have sent, I think, most of you an invitation link. You can also just click and join in this platform. So whenever you have any question, you feel free to post on it. Either I or our TAs will try to answer them as soon as possible. So do not send me emails asking me how to do certain questions. I don't want to answer them through emails. It's not efficient. Post it on this platform so other students can also see them. And also, you are encouraged to answer the questions from your peers. That's also a good practice to help you sort your math out by answering questions. What else? Another thing to clarify is that having asked whether this L1, L2 sections are graded separately, I have to confirm yes, because the two sections we have different exams for different midterm and final exams. So for each section, I probably use a different grading scheme, like to cut off the letter grades. So you don't need to compare it with students from the other section. So I don't have like a hard cutoff. Like if you reach a certain grade, you automatically get A or something. It's based on it's always adjusted based on their level of their exams. So I don't assume a certain hard cutoff for every section. Okay, so for the next content is about the multinomial coefficients. So we talk about the binomial coefficients, that is n choose r. This is a generalization of this binomial coefficient. So the binomial coefficient n choose r is, we can also interpret a number of ways to split these integers or n distinct atoms into two groups with sizes r and n minus r. So this is another interpretation for this number. So the multinomial coefficient is a generalization of this interpretation. For example, now we want to find out that we have n distinct atoms, and we want to divide them into r distinct groups of respective sizes n1, n2, nr. And also, we should sum, if we sum up the sizes, is the total the n distinct items, and we want to find out how many different divisions are possible. Okay, let's work out this problem directly. We provide two proofs. So the first proof is that we count directly. So we first choose group 1. That means we are going to choose n1 atoms out of the n distinct atoms. So a number of ways of doing that is n choose n1. That's to choose group 1. And then we choose group 2. We are going to choose n2 items out of the remaining items, which is n minus n1, choose n2. And for the third group, we are going to choose n3 atoms from the remaining, n minus n1 minus n2, choose n3. So just do it for each group. For the last group, after we have chosen the previous n minus r minus 1 groups, we are left with n minus n1 minus n2 minus nr minus 1. We choose nr out of it. So basically, for the last group, you are left with nr atoms. You just choose all of them. And let's simplify this expression. So it's actually quite satisfying to do this computation, because you have a lot of cancellations. So just write down them as their expression for binomial coefficients. So the second one, n minus n1 factorial over n2 factorial times n minus n1 minus n2 factorial, and then continue this until the last one. Is n minus n1 minus n2 minus up to n minus nr minus 1 factorial. So then denominator we have n minus r factorial, and the difference factorial. So n minus n1 minus up to nr factorial. So this actually equals 0 factorial, because we know that the sum of n1 up to nr equals n. Now we can do the cancellations. You can see this n minus n1 factorial. the numerator from the second term is cancelled with the denominator from the previous term. Then following this pattern, you will see all these numerators except the first term are cancelled, and for the denominators, we are left with n factorial over n1 factorial times n2 factorial times n3 factorial up to nr factorial. And you can check that whether this is correct by considering this r equals 2. R equals 2, we should get back to the binomial coefficient. So you have this, in our computation, we get n factorial n over n1 factorial times n2 factorial. So, and we know that n1 plus n2 equals n. So you can replace one of them with n minus the other number. So it's exactly n choose n1. It's the same as n choose n2 because the relationship between n1 and n2. Okay, so this is a number that looks very, the expression looks very special, and we'll call this number the multinomial coefficient. Before we give the definition, let's also just mention another proof. You can do it in other ways. You can first, let me go over it quickly. So we can think of arranging the n distinct numbers in a line. You have n factorial ways. And for each arrangement, let's see how we define they belong to different numbers. So you can consider the first n1 numbers belong to group 1. So the next n2 numbers belong to group 2, then by doing so. And if the numbers in the first group, these n1 numbers, we don't really care about their ordering. So if you just consider linear ordering of the n numbers, we overcount it. So this coming from the permutation, the ordering of this n1 objects and also for the n2 objects. So eventually, we can use n factorial divide ordering the group atoms from each group, which is n1 factorial times n2 factorial times nr factorial. Okay, that's another way of getting the same number. So this is our formal definition. And assume this n1 plus n2 plus nr equals n. We will define this quotient n factorial over n1 factorial times n2 factorial times nr factorial as this expression we read in a big bracket, this little n on top, and then n1 comma n2 up to nr. This expression, this notation means this quotient. And also maybe let me put how we interpret this number here so it's convenient if you want to refer to it. So this number is the number of ways of dividing n distinct items into r distinct groups. And each group has a size n r, n I. Here, I can be 1 to r. And also, if you sum up their sizes, this is equal to n. Okay, so this is what this multinomial coefficient represents. So for binomial coefficient, that's the case r equals 2. You can also just use the n choose n1, or you can also write this n choose n1 comma n2. It's the same. Okay, let's apply this number to solve some counting problems. Now you can just apply this result directly if it fits in. A police station in a small city consists of 10 officers. If the department policy is to have 5 of the officers patrolling the streets, 2 of the officers working full-time at the station, and 3 officers on reserve at the station. How many different divisions of the 10 officers into the 3 groups are possible? So now with this binomial coefficient, you can interpret this as dividing n officers into 3 groups conducting different tasks, and each group has size either 5, 2, or 3. So this is exactly, the number is exactly 10 choose 5 choose 3. Also, I want to mention that if you permute the number, you write n choose n2, n1, this does not change the value because they have the same expression. So you can further simplify it if you want. Then you can cancel the 5 factorial. You have in the top, you just multiply 10 up to 6, then times 2 times 6. So this is not a difficult number. You get 2,520. The next example is similar. 10 children are to be divided into A team and a B team of 5 each. The A team will play in one league, the B team in another. How many different divisions are possible? So this is exactly, we are dividing the 10 children into 2 distinct groups with labels A and B. So the sizes are 5 each. So it's exactly 10 choose 5, 5. Then this is 10 factorial over 5 factorial times 5 factorial. Gets 252 possible ways. The next example is slightly different. In order to play a game of basketball, 10 children at a playground divide themselves into 2 groups of 5 each. How many different divisions are possible? So it's different because we are dividing the 10 children into 2 groups, but these 2 groups are playing against each other. So if you count like as 10 choose 5, 5, you are dividing the 10 children into group A and group B, but their group names are not important. You can just say one is group A, the other group B, or one is group B, the other group A. It doesn't matter because they are playing against each other. So this means that if you have this number 10 choose 5, 5, you should also divide 2 factorial for promoting the group labels, because which is group A, group B, does not matter now. Okay, so now it's the previous answer divide 2. So I mean, see, the orders, all the labels of the 2 groups are not irrelevant. Okay, so the next thing we want to mention related to the binomial coefficient is this multinomial coefficient is a multinomial theorem. It's an analog of the binomial theorem. Binomial theorem is expanding x1 plus x2 to the power n. Now we can consider expanding this x1 plus x2 plus xr to the power n. And this can be written as this expression, the summation. Each summation looks like x1 to the power n1, x2 to the power n2 times xr to the power nr, with a multinomial coefficient n choose n1, n2, and r in front. And also this sums over all the n1, n2, and r's, which are non-negative integer values, with the constraint that their sum equals n. So just say a few words how to find such an expression. It's very similar to how we proved the binomial theorem. So if you want to expand this expression to the power n, you can think of this as a product of this n brackets. And we'll expand it. Each bracket will contribute 1 copy of xi from it. So in general, we'll have an expression, the summation looks like x1 to the power nr. So we'll have nr x1s taken out of the total n brackets. N. We can have, not nr, n1. We can have n2. X to the power n2, this means that n2 of the brackets contribute x2, and then for xr, it has power nr, meaning that nr of the brackets contribute to xr in the expansion. Of course, these ni's can be 0. So the number ways of choosing n1 x1s, n2 x2s, and r xr's from the brackets is we divide this n brackets into r groups. For the first group, it has as n1, these brackets contribute x1 in the product. And similarly, so you can see the number of ways of getting such a summand is n choose n1, n2, and r, this multinomial coefficient. And also, your sum must be equal to this n. I don't think we'll use this theorem much in this course. So for this theorem, the requirement that you are able to apply it, for example, how to get its expansions, like how can you use this result to expand such kind of expressions. Just for instance, maybe just do 2 exercises to get familiar with how it looks like. Something like that. Maybe it's simpler. Okay. So know how to apply it. That's it. Okay, so the last content for this chapter 1 is we're going to focus on a certain group, a certain kind of counting problem. This can be expressed as finding the number of integer solutions for a linear equation. So let's find out this counting problem. We provide proof here. Actually, this is summarized as theorem, and also I would say this is important, useful little result. So the theorem says there are n-1 choose r-1 distinct positive integer valued vectors x1, x2 to xr. So each xi is a positive integer. And they satisfy this linear equation, x1 plus x2 plus xr, this equals n. So this number, n-1 choose r-1, within this number, this r represents the number of summand. You have x1 to xr. Okay, now all the number of variables in this equation. And this n is the sum of these variables. And also the constraint that xi's are integers, they are positive integers. Okay. It must be integer, otherwise there are infinite solutions. Okay, let's provide a proof for this kind of counting problem. I will show it by the so-called stars and bars methods. We use stars to represent the problem and use bars to solve it. So like we sort of change the problem slightly. We count a different scenario. So actually, this number linear integer solution to this linear equation can be translated in this counting problem. We want to put, now we have n stars into, now because we have x1, x2, xr, let's assume these n stars are, indistinguishable or alike, because we want the xr to be the number of stars later. We put n indistinguishable stars into r distinct bins. You can think of the bins as labels from 1 to r. So it has a label such that no bin is empty. Then this xi is equal to the number of stars in the bin I. the bin with label I. Maybe I call it S bin. Okay. So xi is a positive integer because we assume no bin is empty. Okay, so to find out number of integer solution to this equation is find out how many ways we can put n stars into this R distinct bins such that no bin is empty. So we can always, if you're not sure how to get started, you can always consider a concrete small example. Just say we have n equals 7 stars, and we have R equals 4 bins. Now we are going to, so this corresponds to x1 plus x2 plus x3 plus x4 equals 7. And actually, if we have R equals 4 bins, we are going to use R minus 1 equals 3 bars to separate the stars. So what we do is that we can first line up the stars, 7 stars. Okay. And then we separate into 4 bins. So no bin is empty. So here we are just going to put 3 bars to separate them. So where you can put the bar is you can just put into the slots among the bars. And because the bin cannot be empty, so you cannot put a bar in the top, in the front, or in the end. Otherwise, it'd be empty. So let's see if you put 3 bars here, maybe 1, 2, 3. Naturally, you split the 7 stars into 4 bins. So in this situation, x1 equals 1 star, and this is x2, x3, and x4. So this means that to conduct this test, we just need to put the 3 bars among this. Now we have 6 slots to put the 3 bars. So we just need to choose 3 slots to place the 3 bars out of the 6 slots. So there are, in the example we have, this is 6 slots equals n minus 1 equals 6 slots to place the 3 bars. 3 is R minus 1. And the number of ways is just how many ways we can choose the 3 bars. We can choose 3 slots out of 6 slots. So 6 choose 3, and it is n minus 1 choose R minus 1. And you can generalize from this example. So in general, we have n stars. We put them in a line and consider the slots. The specific, we have n minus 1 slots because we don't want bin to be empty, so we cannot place the bars in the very beginning or in the end. So we have n minus 1 slots to play R minus 1 bars. So the number of ways is this n minus 1 choose R minus 1. From a total of n minus 1 slots. Place. Okay. So the number of ways is what is given. N minus 1 choose R minus 1. Okay, hope this makes sense. Okay, so you can use this result directly if you find it that your counting problem can be translated into this kind of integer solution problem. Another related result, let's also phrase it as a theorem, is this one. So it's a similar problem, but now the restriction is different. Now we are considering non-negative integer solutions of the same equation. So now it's non-negative, so it can be 0. So number of non-negative integer solutions for this linear equation, x1 plus x2 plus xr equals n. So the sum is still n. The number of variables is still r. But now the xi's can be zeros. So the xi's are now non-negative integers. So still. And for this problem, the number of solutions is n plus r minus 1, choose r minus 1. So there should be more solutions if your xi's can be zeros. So this is also an important result, and you can also use it directly. Okay, so I will provide two proofs. The first one is algebraic. Actually, I think it's more natural because you can translate this counting to the previous positive integer value problem by a translation. So because xi's are non-negative integers, so if you consider xi plus 1, this will be positive. So we'll use new variables. We let the yi equals xi plus 1. Then the yi's are positive integers. And we count the number of integer solutions in terms of yi's instead of xi's. Now we also translate this given linear equation in terms of linear equation of y. So each xi equals yi minus 1. And plug into this given equation, you get y1 minus 1 plus y2 minus 1 plus yr minus 1 equals n. In total, you subtract r once. So you can write it as y1 plus y2 plus yr equals n plus r, where the yi's are positive integers. So number of solutions by applying the previous result is the sum now become n plus r. This is minus 1. Choose this number of variables minus 1. Choose r minus 1. So you get this result. Okay, and also just to be consistent, I also provide a direct counting using the star and bars methods. Let's do a direct counting. So it's the same as we put this n like stars into R distinct bins. So R bins, you can label them from 1 to R. So now the difference is that now the bin can be empty. And still, if you let xi to be the number of stars in the S bin, then we know that the sum of xi's to x1 plus x up to xr equals n, and also the xi's are non-negative integers. So these two problems are equivalent. So now we need to figure out how we are going to arrange the stars and the bars such that we can accomplish this task. We can also just think of like small examples to help us understand how we can make this work. Say we have 5 stars and R equals 3 bins. And this always corresponds to R minus 1 here equals 2 bars. Now we can see we want to check how we can arrange the stars and the bars such that this will work. So maybe I draw some examples. So we have 5 stars. Okay, so maybe I just copy them a few times so we can place the bars. Okay, so of course you can put the bars here and here. This means, so the equation is x1 plus x2, x3 equals 5. So here, if you place a bar in the first configuration, x1 equals 2, x2 equals 1, and x3 equals 2. And now the bins can be empty. So you can also just consider extreme case. You put 2 bars here in the very beginning. This means x1 equals 0, x2 equals 0, and x3 equals 5. And of course, you can also place the 2 bars like this next to each other. This means x1 equals 3, x2 equals 0, and x3 equals 2. And you can think of all these configurations like this. So basically, from this small example, it's basically if we want to place the stars into our bins like this, it's just arranging the 5 stars and 2 bars in a line, okay, arbitrarily in a line. Just put these 7 objects into a line, okay. And we just need to count that some of the objects, the bars are alike, stars are alike. So now we are not like first place the stars in a line and then put the bars in the slots. Now we consider them together. We arrange these 7 objects together in a line. So, so how to solve it is we arrange this n alike stars and r minus 1 bars. So together in a row. Okay, and find out how many arrangements are possible. So number of such arrangements so you can actually use the previous result directly. You arrange m objects in a line, some of them alike, few of them alike. So also you can just solve directly. So in total, we are arranging n plus r minus 1 objects into a line. If they are all distinct, then we have n plus r minus 1 factorial ways. And because some of them are alike, we divide their permutations among the alike items. So we are going to divide n factorial times r minus 1 factorial. So this gives us this binomial coefficient as a result. Okay, so that next, let's use these two kinds of results to help us to solve certain counting problems. Now we can solve them in a faster way because the formula available. So in this example, an investor has $20,000 to invest among 4 possible investments. Each investment must be in units of $1,000. If the total $20,000 is to be invested, how many different investment strategies are possible? The second question is, what if not all the money need to be invested? Okay, so let's try to relate to a solution of linear equations. So we have the 4 possible investments. We are going to denote the xi to be their number of thousands. So maybe 5,000 or 10,000 is their values of xi. In investment I. So I can be 1, 2, 3, 4. Okay, so in the first question, if all 20,000 are invested, this means that if you sum the investment for each 1, 2, 3, 4 investments, the total number is 20. So sum xi equals 20. And also, we don't have other restrictions. So xi's, so because each investment must be in units of $1,000, yeah, integers. For each xi. So this is exactly the linear equation with solutions non-negative integers. So the number of different number of possible investment strategies we can just use a formula just choose a non-negative solution, which is n plus r minus 1, choose r minus 1. Here our n equals 20, the sum, and r is the number of variables, equals 4 here, and plug in, you get 23, choose 3, and then if you want to find the exact value, it's 1,771. But if you just leave the answer like 20 to 3, that's perfectly fine. And for the second question, if not all the money, if not all the 20,000 need to be invested, so you may have some money left. Okay, so one way is to consider different cases. You use up all the 20,000, or use 19, 18, 17, like this. You can see this is more complicated. But now let's still try to relate this to a linear equation. So we introduce another variable. We let x phi be the number of thousands kept in reserve. So this is the part of money not to be invested. So we still have linear equation. Now we have x1 plus x2 plus x3 plus x4 plus x5 equals 20. Okay, so we don't need to consider different cases now. And also, these xi's are still non-negative integers. And we can just use the formula to solve directly with the number of possible ways for investment. Is this n plus r minus 1, choose r minus 1 now. In this setting, this n is still 20, but r is changed to 5. You can plug in, you get 24, choose 4. And this is a larger number. Okay, so last example for this chapter, still we go back to the same example we mentioned last time, arranging these antennas so we have a working system. So we have in total n antennas. Among them, m are defective, n minus m are functional. And we don't want two defective ones to be next to each other. And of course, to assume all the defective and functional ones are considered indistinguishable. We want to find out how many linear orderings are possible such that no two defective ones are consecutive. So previously, what we do is that we first place the functional ones in a line and look at their n minus, so there are n minus r, n minus m functional ones in a line, and it creates n minus m plus 1 slots among them, and then we place the m defective ones in their slots. So basically, we just need to choose m slots among the slots created by the functional ones slots. So the answer is n minus m plus 1, choose m. Now we can solve it in a different way. So here I just get a little started. And I want you to finish it yourself. I will put this complete solution to Canvas later. So this time we can first line up the defective ones. So let me use the cross box. There are m of them. And we have the functional ones. I use a circle. And there are n minus m of the functional ones. So first we can, this time we consider placing the defective ones in a line. So there is only one way because they are alike. Then we insert the functional ones among these defective ones, such that no two defective ones are next to each other. So assume you insert some functional ones here. Maybe I'll label, I will just call this, because we have m defective ones. So you insert some functional ones in between them. Okay, and then I will call this, maybe I'll call this, this is the first position, and this is the second position, and like that. And denote the number of functional ones in the first position as x1, and their number of functional antennas in the second position as x2, then x3. Then you have this is xm, then xm plus 1. So in order to make this configuration work, you need to assume something about xi's. So the x1 can be 0, it's bigger or equal to 0 because it doesn't matter. But for x2, it has to be positive because you don't want this 1, 2 together, defective ones. So you're going to put the constraints like that and relate this as their linear equation and try to use the formula to solve it. So I'll leave the remaining as an exercise. Okay, I will go over it briefly next time. Okay. So that's all for today. See you guys next week. Oh, by the way, I will not give attendance check on February the 16th because we have a class in the morning, but it's right before the Chinese New Year. So I think many students may have traveling plans, so I'm not going to give attendance check on that day. So.